presentation of the work entitled Performance Evaluation of Industrial Internet of Things Services in Devices of Cloud Fog Do Things Computing at SBESC 2020. The rise of Internet of Things will contribute to a continuous increase in the volume of data generated by the factories, which will produce an overwhelming data flow called big data. Big data is transforming the industry, and the significant challenge is that data growth exceeds the ability to design appropriate cloud computing platforms for data analysis and workload updating. Fog computing has recently attracted interest in its potential to satisfy requirements that are not met by cloud computing. The fog extends the available resources to the edge of the network to support Internet of Things solutions. Despite the benefits of decentralized cloud through fog computing, Internet of Things devices have processing and communication performance requirements that cannot be easily met by cloud and fog devices. Because punctuality can be strongly affected by unpredictability, real-time systems are primarily susceptible to performance challenges. With the recent arrival of the dual computing, the communication link distance will be shorter, which will significantly increase the performance of the network. However, this proposal must be evaluated and analyzed. Dual computing is based on different types of equipment, from smart devices like smartphones to smart sensors and actuators, consisting of several microservices that can collaborate with the cloud or fog. Dual computing is currently applied in heterogeneous, wireless, sensor network management, object tracking, healthcare, streaming, and Internet of Things. Such works apply the dual computation in different areas through different devices. However, none of these studies assess in practice the performance of dual computing in the industrial context. In this context, we present and develop a proof of concept to measure aspects of processing and communication of industrial services in the cloud, fog, dual, and Internet of Things. For this assessment, an Internet of Things communication system was developed. The system consists of a robotic arm that needs to move specific objects located on your desktop to a target area. In this scenario, it is considered that the device that controls the robotic arm depends on devices from the cloud, fog, dual, or Internet of Things to carry out its activities. Internet of Things devices have been classified into two classes of processing and memory: high-performance Internet of Things devices and low-performance Internet of Things devices. The proof of concept was evaluated in real tests performed to measure the total time of network time and execution of services in devices of cloud, fog, dual, and Internet of Things. Two metrics are evaluated: the processing delay for each device to perform a service, and the network delay for communication between each device. The following table shows the device specifications, distance between devices, and the network configuration. A Wi-Fi router intermediates the communication between the devices. Dual and Internet of Things devices use wireless communication, while cloud and fog use wired communication. We repeated the tests 100 times, and the data of the results were obtained through calculations in the application of the robotic arm, with a confidence interval of 95%. Two types of services are performed: inverse kinematics for calculating the movement of the robotic arm, and image processing to identify objects in the work area. In the first and second experiments, we evaluated the network and processing delay considering only one client at a time. The results of the first experiment show that the fog device has the best performance for the performance of inverse kinematics services. Due to the hardware characteristics and proximity to the robotic arm, the fog device was able to calculate the inverse kinematics in half the time of the dual device, which was the second device with the best performance. The results of the second experiment showed that the cloud device presented the best performance for the execution of image processing services. However, the time difference between cloud and fog devices was only 138 milliseconds. In addition, network time is considerably low for all devices except the cloud device, that spent 35% of the time transporting messages. In the third and fourth experiments, we evaluated the network and processing delay considering several simultaneous clients. The results of the third experiment indicate that the network time increases according to the increase in customers requesting the services simultaneously. In this case, the devices that perform the services have a more massive workload with a larger number of clients, and therefore the communication channel is busier with more packets at the same time to be transmitted and processed. The results of the fourth experiment show that the device with the best performance to run the image processing service was the cloud device. The processing time was the one that most influenced the execution of image processing services for all devices. In addition to the cloud device, only the fog device provides efficient image processing service execution for up to 10 client devices simultaneously. The result showed that the dual computing devices have low network performance, especially for image processing. Low performance of dual and Internet of Things devices is related to wireless technologies that are limited in communication range and bandwidth. Another significant challenge in adopting dual computing is the integration of asynchronous systems with process control systems and synchronous field devices oriented in real time. In many situations, these devices have very severe time restrictions. Within the industrial context, dual computing can promote strong decentralization, covering many nodes, logically positioned at various hierarchical levels and distributed over large geographic areas. In this context, the consensus between the dual nodes becomes essential for communication to be safe and reliable. The blockchain can decentralize and support decision-making in a factory's internal and external process. Thus, dual computing in conjunction with blockchain can make industrial automation systems fully decentralized, automated, and reliable. Despite the advantages of blockchain, evaluations of this technology show that even on servers, blockchain networks present time and variation problems for the processing of Internet of Things data. Also, hosting blockchain directly on Internet of Things devices is unadvisable for the following reasons: lack of resources for cryptography and basic tasks such as mining, lack of sufficient bandwidth to replicate and maintain the blockchain, and the necessary energy savings. Finally, it is expected that new generations of dual and Internet of Things devices will be equipped with better hardware specifications, which will allow for shorter response times when performing services.